today's topic is Sharpless asymmetric epoxidation. This topic comes under the chapter addition of carbon-carbon multiple bonds. So let's start. KB Sharpless and co-workers reported a method that has since become one of the most valuable tools for chiral synthesis. The sharpness or asymmetric epoxidation is a method for converting allyl alcohol to chiral epoxy alcohols with very high enantioselectivity. Here, enantioselectivity means that it prefer in enantiomer over forming a racemic mixture. So it involves treating the allylic alcohol with TBHP, titanium isopropoxide, and a specific stereoisomer of tartrate ester. The esters most commonly used are positive or negative dextrolivo, diethyl or diisopropyl tartrate. The tartrate stereoisomer that is chosen depends on specific enantiomer of epoxide desired. The main feature of this Sharpless epoxidation procedure is that it affords a single enantiomer of epoxide at high enantiomeric axis. Here, as you can see, when the positive DET is taken, the product form is cis. And when negative DET is taken, in the product, the trans structure is formed. The S and R are the configuration of methyl glycidol. This method can be applied to both primary and secondary allylic alcohols. Here let's start about the mechanism of this reaction. The precise course of reaction is not entirely clear, but the rate of acceleration and the high stereoselectivity observed suggests that the formation of an intermediate in which allylic hydroxyl group is coordinate of metal. Here, as you can see in this compound, when we treat it with BuTOH and when we treat with this compound with titanium isopropoxide, then the product form, as you can see, this is same as of peroxide mechanism. Here it formed three-membered intermediate state. It seems to be generally agreed that the transfer of oxygen to double bond takes place in a titanium ester in first structure conformation, which minimize the steric interaction among various substituent groups because it form here a group. As you can see here, this oxygen's lone pair bond with here and this lone pair goes to lone pair here. So the structure become this. It forms a ring here over, and when the rearrangement takes place, this become this. So a number of different models have been proposed to account for the observed stereoselectivity of the reaction, one of which shows allylic alcohol being forced to adopt conformation in which one phase is preferentially exposed to the oxidant. Here is the structure. It shows that if allylic alcohol is drawn so that the hydroxyl group is at lower right. Here E is the ester. Oxygen is delivered at the bottom phase in presence of positive DET, from top phase in presence of negative DET. So that's all for today's video. See you guys in the next video.